In this video, we'll talk about the notes for section 3.3, which is called classical Fourier series. The so-called classical Fourier series is the one that was an orthonormal system composed of sines and cosines. It's also known as a trigonometric series. If f is an integrable function, not of, but this should say on, the interval from minus L to L, then its classical Fourier series is the one that looks like what you see here. A0 over 2 plus the sum going from n equals 1 to infinity of an times cosine of n pi x over L plus bn times sine of n pi x over L, where an and bn are the Fourier coefficients. So an is equal to 1 over L times the integral of minus L to L of f of x times cosine of n pi x over L dx, and bn is equal to 1 over L times the integral from minus L to L of f of x times sine of n pi x over L dx. When you integrate f against the cosine, the idea is that if f has this Fourier series, then when you integrate against cosine of n pi x over L, the integral will cancel for all of these sine terms and all of the cosine terms except for one, because these sines and cosines form an orthogonal system. So here's the orthogonal system here, 1/2. That's really cosine of 0, so that's the case where n is equal to 0. We don't consider the case where sine has n equals 0 because sine of 0 is just 0. But we do consider the case for cosine where n is equal to 0, and that's really where this 1/2 comes from. Remember, we have a 1/2. The reason there's a 2 in the denominator is just so that the formulas work out right. So this set of functions, 1/2 and then cosine of n pi x over L and sine of n pi x over L, these are an orthogonal system. And we showed that before. We actually looked at all of the necessary integrals. To make the system orthonormal, we divide each function by its L2 norm. And if you compute the L2 norm, what you'll find, well, if we just look at the integral of cosine squared, you end up with L. And similarly for sine, if you integrate sine of n pi x over L quantity squared from minus L to L, you'll still get L. So that means the L2 norm of both of these is the square root of L. So in order to have an orthonormal system, we just need to divide everything by the square root of L. I forgot to normalize the constant term here. This shouldn't be 1/2 anymore. You need to divide it by its size. So this should actually end up being 1 over the square root of 2L, like so. That's easy enough to show. So remark, if you just compute the L2 norm of 1/2, well, let's square it. That's going to be the integral from minus L to L of 1/2 squared dx, which of course is 1/4 times 2L, which is L over 2. So the size of this thing is the square root of L over 2. So if you take 1/2 and divide it by its size, that's 1 over the square root of 2L. So that's why here we have 1 over the square root of 2L. So this is an orthonormal system in L2, and it's also a complete system, but we won't actually show that. When it comes to defining the Fourier series, we don't write out the orthonormal system, we just write the orthogonal system. So cosine of n pi x over L, sine of n pi x over L, and just this term, the 1 over 2. We don't need to worry about the fact that it's orthonormal because when we look at the formulas, that's built into it. It's built into it that we haven't normalized everything. That's why you have all of these 1 over L's here. That's actually why there's a 2 there to begin with. Okay, so the fact that we're just looking at this orthogonal system that we haven't normalized, that's why these formulas look the way that they do. Okay, so we have an orthonormal system, and we define a Fourier series in terms of the orthogonal system. And since we know that the system is complete, or at least we're taking it for granted that it's complete, that means that the Fourier series converges to the original function, at least in the L2 sense. So let's give some definitions. So suppose we have this Fourier series. So the term that we're summing here, the summand, an times cosine of n pi x over L plus bn times sine of n pi x over L, we call that the nth harmonic. Each harmonic has a higher frequency than the previous one. The frequency spectrum of the series is the sequence gamma n, where gamma n is defined as follows. So for n equals 0, of course, it will have a different definition. So gamma 0 is the absolute value of a0 over the square root of 2, and gamma n is the square root of an squared plus bn squared. So this is a measure of the contribution of the nth harmonic to the decomposition of f. So notice that we're really measuring the size of the nth harmonic here, in some sense. So these numbers, gamma n squared, form what is called the energy spectrum of f. And in this context, we can rewrite Parsifal's identity, and it looks like what you see here. So it's 1 over L times the L2 norm of f squared is equal to a0 squared over 2 plus the sum n equals 1 to infinity of an squared plus bn squared, which is really just the sum of the elements of the frequency spectrum squared. So if you square all of these terms and add them together, that's the thing on the right. And that equals, according to Parsifal's identity, 1 over L times the L2 norm of f squared. It's easy enough to show based on Parsifal's identity that we've already seen. You just rephrase it in this context. So let's work through a few examples. For our first example, let's find the Fourier series for the function f at x equals x on the interval from minus L to L, where L is some positive number. So we know what the Fourier series of f looks like, and we have formulas to compute the coefficients, so let's just go ahead and compute those coefficients. So first let's look at the ANs. So in order to compute the ANs, we integrate f against the cosine functions. Now here we're going to use a certain fact to make our lives a little bit easier. X is an odd function, and cosine is an even function. So if you take an odd function times an even function, you get an odd function. And if you integrate an odd function over a symmetric region from minus L to L, for example, you just get 0. Everything cancels. So that's going to cut our work in half. In order to compute Bn, we can make things a little bit simpler by using the fact that an odd function times an odd function is an even function. So here, again, x is an odd function. Sine is an odd function. So if you multiply two odd functions together, you get an even function. And if you integrate an even function over the symmetric interval from minus L to L, then that's the same as twice the integral from 0 to L. Because an even function is symmetric about the y-axis, so everything to the left of 0, everything to the left of the y-axis, when x is 0, everything to the left is the mirror image of everything to the right. So we just need to integrate from 0 to L and then double it. That just makes the computations a little bit easier. So here we're integrating from 0 to L x times sine of n pi x over L dx. Okay, so this is a case where we want to use integration by parts. I won't go through all of the details, but that's what this statement is. We let u equal x, and we let dv be sine of n pi x over L dx, and then we just use the usual formula. And once you simplify it, so you compute the antiderivative. This is the antiderivative. You evaluate it from 0 to L, and you end up with this expression. Notice that sine of n pi is always equal to 0. Cosine of n pi is minus 1 to the n. So this all simplifies quite a lot, and you just end up with 2l over pi times minus 1 to the n plus 1 over n. Now there's an n plus 1 there because there's an extra minus sign there. So that's negative 1 times negative 1 to the n. So that's where that comes from. So that tells us that the Fourier series of f is the sum, n equals 1 to infinity, of 2l over pi times minus 1 to the n plus 1 over n times sine of n pi x over l. There are no cosine terms here because all of the an's are 0. And this is because f is an odd function. So if f is an odd function, we can write it as a sine series. And that's not totally surprising because all of the sines are odd. So if f is an odd function, it's not surprising that if you're going to write it as a trigonometric series, you can find some way to write it as a trigonometric series where all of the terms are also odd. They're all sines. Here's another example. Let's find the Fourier series for f at x equals the absolute value of x on the same interval from minus L to L. So this is an arbitrary symmetric interval from minus L to L where L is some positive number. So again, the Fourier series of f is given by the usual formula where an's and bn's are computed using integration against sines and cosines. So again, we're going to use the same sort of facts to make the computations a little bit easier. The absolute value of x, that's an even function. So an even function times an odd function, like the sine term, an even function times an odd function is an odd function. So again, if you're integrating an odd function over a symmetric interval, you get 0. Because everything to the right of the y-axis is not exactly the mirror image, it's the double mirror image through first the y-axis, then the x-axis. So everything that gives you, say, positive area on the right, there's something corresponding giving you the opposite of that on the left. So everything cancels. Although we're really thinking of that as signed area, not area exactly. So that tells us that all of the bn's are 0. Well, what about the an terms? These won't all be 0. So a0, we usually need to compute a0 separately. So a0 is 1 over L times the integral from minus L to L of the function f. Really, it's just where n is equal to 0 here in this formula. But since n is equal to 0, that term just disappears. Cosine of 0 is 1. So we're integrating, again, an even function over a symmetric interval, so we're going to write that as twice the integral from 0 to L. Now this is just x to the 1, so we just use the power rule, that's x squared over 2. The 2's cancel. You evaluate between L and 0, so you end up with L squared over L. This L in the denominator cancels with 1 in the numerator, and you just end up with an L. So that tells us that a0 is L. A sub n, we use the same sort of technique. 1 over L times the integral from minus L to L of the absolute value of x times this cosine term, dx. Now we have an even function, the absolute value of x, times another even function, this cosine term. So an even times an even is still an even. So that means we're integrating over an even function over a symmetric interval, so it's twice the integral over 0 to L. Once again, we want to use integration by parts here. So now u is equal to x, but dv is this cosine term. But otherwise, it's very similar. Then you get the antiderivative, then you evaluate at the endpoints, compute the difference using the fundamental theorem of calculus. You end up with these terms. Again, you have a sine of n pi, that goes away. You have a cosine of 0, which is 1. There's also a sine of 0 term. So when you plug in the 0, you get 0 times sine of 0. I didn't even bother writing that one down. Here we have a cosine of 0. Cosine of 0, of course, is 1. And here we have a cosine of n pi, which is minus 1 to the n. So if you collect all of these terms, well, you get rid of the sine term, just write that as 1. You have L squared over n squared times pi squared times minus 1 to the n minus L squared over n squared times pi, which is this term here. So this term is equal to 0 if n is even, because if n is even, then minus 1 to the n is 1. so this term will go away. Now on the other hand, if n is odd, then this becomes a minus 1 is minus 2. So you get a minus 2 times 2 is negative 4L over n squared pi squared. So that means we can disregard all of the terms where n is even, and you just end up with these odd terms. So you have L over 2, so that's A0 was L, A0 was L, and so you divide it by 2. So you have L over 2, plus the sum, k equals 1 to infinity, and we switch the index to k here. We want n to be odd, so basically the idea is we're letting n be equal to 2k minus 1. So as k goes from 1 to infinity, that cycles through all of the odd numbers. So when k is equal to 1, this is 2 times 1 is 2 minus 1 is 1. So that corresponds to the k equals 1 case. So we just replace all of the n's with 2k minus 1. So we've done that here and also here. So that's that. Okay, so notice here that f is an even function, so we're writing it as a cosine series. Cosine series. All of the terms here are even. This is a constant term. Constant terms are certainly even. So if f is an odd function, you can write it as a sine series. If f is an even function, you can write it as a cosine series. For our next example, let's let f at x be a unit step function. So f at x is equal to 0 until we get to 0, and then it jumps to 1 when x is 0, and it's equal to 1 after that. So this is actually the Heaviside function, just restricted to the interval minus L to L. So it's the unit step function. So let's go ahead and compute the coefficients. A sub 0 is equal to 1 over L times the integral of f at x. Now, of course, this function, f at x, is 0 until you get to 0, and then it becomes 1. So anytime you integrate f, you can ignore the interval from minus L to L, or not minus L to L, minus L to 0, because the function f is 0 at that time when x is negative. So we just need to look at the integral from 0 to positive L. So that's 1 over L times the integral from 0 to L of 1. But if you integrate 1, you just get x from 0 to L. That's just going to give you another L. So you'll have 1 over L times L, which is 1. Now what about an? So it's 1 over L times the integral from minus L to L, again, of f times the cosine term. But since you're multiplying by f, it's 0 when x is negative. So this just reduces to the integral from 0 to L times 1 times the cosine term. So if you integrate cosine from 0 to L, you'll get some kind of sine. So we just have to divide by the constants in here. So you divide by n pi over L, that's why we're multiplying by L over n pi, times sine of n pi x over L. Now here, when x is equal to L, you'll get sine of n pi, which is 0. And when x is equal to 0, you'll get a 0 here. Sine of 0 is 0. So you just get 0 minus 0, which is 0. So all of the an terms go away, save a sub 0. So that one doesn't go away. What about the bn's here? So that's integrating, so that's 1 over L times the integral from minus L to L. Again, you're multiplying by f. So that's going to be 0 for negative x. So you just end up with the integral from 0 to L of the sine term. So you integrate that, and you get the opposite of cosine. And again, you divide by the n pi over L, so that's why that L over n pi is there. So that L cancels with that L, so you just have minus 1 over n pi. Now what about the inside here? So, inside these brackets. So when you evaluate this term at x equals L, the L's cancel and you end up with cosine of n pi. And when x is equal to 0, you just have cosine of 0, so that's 1. So we end up with the same sort of thing that we saw before in the last example. So when n is even, you have minus 1 to the even number is going to be 1, so you have 1 minus 1 is 0. So this is 0 if n is even. If it's odd, then you'll get minus 1 minus 1, so that's a negative 2, times this term out in front. So negative of a negative is a positive, 2 over n pi. So it's 2 over n pi if n is odd and 0 otherwise. So we have this a0 term. So a0 is 1, so that's why there's a 1 right there. That's the a0 term. And then it's plus 2n pi. But again, we're just looking at the case where n is odd, so we'll just write n is equal to 2k minus 1. And that's why we have a 2k minus 1 there and a 2k minus 1 there. So the coefficient, of course, is 2 over n pi. So 2 over pi, and then the n becomes 2k minus 1. And then it's times the sine term. Now there are no cosine terms here because the an's are all 0. But the bn's are not all 0. So that's why you have sines here. Now this is not an odd function on this interval. This is not an odd function. And it might look like a sine series, but this 1/2 prevents it from being a sine series. This 1/2 is what stops it from being an odd function, because the sine functions are all odd. So this 1/2 term is part of the cosine series. So there is one cosine term here. It's just you don't see it because cosine of 0 is 1. It's the n equals 0 case. Let's look at some graphs. So this was the first example that we looked at. So when f at x was equal to x. Now in this case I'm setting L is equal to 1 just because it's a little harder to graph using a computer if you don't actually put in a number. So let's look at the case where L is equal to 1. So this is f at x equals x, so this is our first example. And in that case, you just set L equal 1 and you get f at x is equal to this sine series here. The sum n equals 1 to infinity of 2 over pi times minus 1 to the n plus 1 over n times sine of n pi x. So let's graph this for a few choices of n, not in other words, how many terms we're adding together. So here we're going to just add in one term. So that if you just add in one term, n equals 1, then it's going to be 2 over pi times minus 1 squared, so that's positive 1, over 1. So it's going to be 2 over pi times sine of pi x. So this is just 2 over pi times sine of pi x. So it's a sine function. It looks like a sine function, as you can see here. Now if you start adding terms to that, so here's n equals 3. Now you can see that it starts losing its sine behavior. And even with only n equals 3, it does sort of start looking like y equals x, at least right here. Right here. Notice we're only looking at the interval from minus 1 to 1. Minus 1 to 1 is this interval here. So minus 1 is minus 1 is right about there, and positive 1 is right about there. So we're just really looking at this interval here. Now, of course, sine is periodic. So all of these sine terms are going to be periodic. So the Fourier series, as a result, is going to be a periodic function. So if you start plotting the Fourier series, you're definitely going to start seeing periodic function here. Now we're restricting our attention to minus 1 on the interval from minus 1 to 1, and that's what we have here. Now you'll notice that I don't include the x equals 1 term in my interval. We'll talk about that later, but basically it has to do with periodicity. In order for this to be a periodic function, with period 2 in this case, the period is 2L. So with period 2, we need to start and end at the same spot. So that's why we don't include the 1 here. But we'll talk more about that after we look at these examples. So we're really just looking at our function f. We're trying to approximate it using this part of the graph. And you can see already it kind of looks like y equals x. If you jump up to n equals 10, you can see that you can still see some oscillating behavior, but it's really getting straight. And if you go up to n equals 100, it really looks like a straight line. Now notice these lines that look almost vertical here. Now they're not actually vertical lines. There is a line that is, or a curve I should say, that is connecting this peak to this valley. The sine series, we're adding together 100 terms, But every one of those terms, let me just scroll back up to where we see the series here. Every one of these harmonics here is continuous. So when you add together 100 of them, it's still a continuous function. So what you're looking at here is the graph of a continuous function. Now it just goes from up here around 1 to down here around -1 so rapidly that the computer can't figure out exactly how to graph it, so it makes it look like a straight line is there. This is actually not a straight line. It's a curve, but it's too difficult for the computer to graph that. So that's with n equals 100 terms, and look how accurately that represents y equals x. Let's take a look at this series, the absolute value of x. So here we're going to look at the case where L is equal to 1. So that means we're looking at the interval from -1 to 1. Again, I'm not including both endpoints, just for periodicity reasons. So we computed the Fourier series, and if you just look at n equals 1, so if we have n equals 1, that's going to be 1/2 plus the first term here when n equals 1. So when n equals 1, this is in the denominator. I was calling it k earlier, but so n equals 1, this is 2 minus 1 is 1, so this term disappears. So you just have -4 over pi squared times cosine of pi x. And so this is a cosine. Notice it's shifted up by 1/2. This constant here is less than 1. So you'll notice it doesn't actually reach the x-axis here. It's hovering slightly above. So that's n equals 1. So it's going to be 1/2 plus some constant times a cosine. Now if you look at n equals 3, notice that you start getting the traditional V shape that comes from the absolute value of x. It's not perfectly straight, and you still have this periodic behavior, you still have oscillations, but even with n equals 3, it's very close to the absolute value of x, in appearance at least. Notice it's still hovering above the x-axis. Now by the time you get to n equals 10, it's really difficult to distinguish this portion. So again, we're just looking from -1 to 1. So we're just, this portion looks very much like the v of the absolute value of x, and when you have n equals 100, it's very difficult to distinguish that from the absolute value of x. Now, we know that a Fourier series converges to its function in the L2 sense, but what you're seeing in these graphs is, in these examples, it's also converging pointwise. Pointwise just means that for every value of x, the numerical values converge. And you can see from this picture that the graphs are starting to look like y equals x in the first case, y equals the absolute value of x in this case. That's representing the fact that this is convergence pointwise as well as in the L2 sense. So for these examples, not only do we have L2 convergence, mean squared convergence, we also have pointwise convergence. Now that's not something we've proved, we're just observing it in the graphs. We looked at one other example, which was the Heaviside function, or the unit step function. And we saw that this was the formula. Again, we're looking at L equals 1. So maybe I'll just put L equals 1 like I did on the others. L equals 1. So this is the form that the Fourier series takes. And if you just plug in n equals 1, this does not look particularly like a step function. It looks like a sine function, as it should. It's 1/2 plus the sine function. But even at n equals 3, you start seeing something that looks a bit more like the unit step function. Again, we're only interested in this interval from -1 to 1 at the moment, at least. -1 to 1. And you can see that it's hovering around 0. It's oscillating, but it's oscillating around 0 for negative values between -1 and 1. And then it jumps. Once x becomes positive, it jumps up to around 1. Again, it's oscillating, but it's oscillating around 1. And when you get to n equals 10, it's still oscillating here. It has to oscillate. It's 10 sine terms. You're adding together 10 sine terms. So it's still oscillating, but it's oscillating right around -1 and then 1. And with n equals 100 terms, you can still see some waves, a little noise here, but it looks very much like the unit step function. Again, we're just looking at this interval from -1 to 1 right there. Now these are all continuous functions because I'm adding together finitely many continuous functions. Here we're looking at n equals 0, not n equals 0, n equals 100. So that's a lot of sine functions that I'm adding together, but they're all continuous, so the result is continuous. So when you see these straight lines here, these aren't representing vertical asymptotes or anything like that. There actually is a curve here. It's just that the computer tries to draw it, and it happens so rapidly. It jumps from 0 to 1 so rapidly that the computer interprets that as what looks like to us a straight line, a vertical line. Let's do another example just for fun. So this is the example f at x equals x when x is between -pi and 0, and it's 0 between 0 and pi. So in this case, we're choosing L to be equal to pi, so the length of the interval is 2 pi. So I wanted to do an example that where the coefficients didn't all cancel, so that's why we're doing this example here. So we let f at x be, it's x from -pi to 0, and then it's 0 after that. So we at least have the function 0 half the time just to make the computations a little bit easier. Okay, so a sub 0 is 1 over pi, because again L is equal to pi, so that's 1 over pi. So it's the integral from, well, we don't have to worry about the integral from 0 to pi, because when x is between 0 and pi, f is equal to 0. So it's just the integral from -pi to 0. So we're just integrating x. So that's x squared over 2. So that's going to result in a 0 minus pi squared. So that's why there's a minus pi squared here, divided by 2 pi. So it's just minus pi over 2. Then we have an for n greater than 0. So that's going to be 1 over L times the integral from minus L to L. So it's minus pi to pi. But again, f is 0 when x is positive. So it's just minus pi to 0. So once again, we want to do integration by parts. So I won't go through the details. But in the very end, you'll end up with something like what we've seen before, 1 over pi n squared times 1 minus -1 to the n. Now, once again, this is equal to 0 if n is even, and minus 2 over n pi squared if n is odd. Now, I'm not going to make the same change of index that I did before, because I want to keep the harmonics together, and we're not going to see exactly the same behavior for the bn's. So if you look at the bn's, we're integrating, again, it's from minus pi to 0 of x times sine of x, or sine of nx. So again, we use integration by parts, and in this case, we'll end up with a cosine of minus n pi, which is the same as cosine of n pi because cosine is even. So that, of course, is a minus 1 to the n. So we don't get that same behavior where half the terms are 0. So since I want to keep the harmonics together, I'll just keep this term like it is. So that's right there. Let me just, so this term is that term right there. And we have this n over pi squared, which you see there. So it's multiplied by cosine of nx. Now, the reason why you have all of these nx's here is because L is equal to pi. So all of these things should be n pi x over L. But since L is equal to pi, you get some cancellation, so it just becomes n over x here. And then we also have this term minus 1 to the n plus 1. That's right here. That's that term. And then that n is the same as that n. Now we of course also have the a0 term. The a0 term is minus pi over 2, which you see here, but of course you have to divide it by 2 as well, because the first term is a0 over 2, so that's why it's minus pi over 4 instead. Now you could rewrite this so that you could just replace all of those n's with 2n minus 1, because that just gives you all of the odd terms. And none of the even terms, because we know it's 0 when n is even. But I wanted to keep the harmonics together, so I'm just going to leave it like this. So let's make some remarks. Now I've commented on some of these already, but let's just organize them all together. So for our first remark, in each example, the function f was defined on the interval from minus L to L, including the left endpoint but excluding the right. So in the plots, L was equal to 1. So the Fourier series is necessarily periodic with period 2L. So the Fourier series represents not just a Fourier series for a function, but the periodic extension of f from minus L to L to minus infinity to infinity. That is, we define f in this interval from minus L to L, and then define f outside of that interval so that f at x is equal to f at x plus 2L. So define it so that it's periodic. That's the periodic extension. And we do that for all x and r. So note that in this case, that implies that f at L is equal to f at minus L, because if you add 2L to minus L, you get L. So f at minus L plus 2L is equal to f at L. And since f is periodic, these two things have to be equal. So that's why in these examples I was excluding the right endpoint, because if you define them so if, for example, you define f at x equals x, then of course f at minus L is equal to minus L, and f at positive L is equal to L. So these aren't equal, but you want them to be equal. So what I did is just excluded that one, and I just defined it to be a periodic extension. So we want f at L to be equal to minus L because we want these two quantities to be equal. So that's why I was excluding the right endpoint on these intervals. So that's our first remark. Our second remark is also something that I mentioned. The function f may not be continuous. However, for any n, if you look at this partial sum, where k goes from 1 to capital N, that's a finite sum of continuous functions, and so it's necessarily continuous. That means that we can approximate any L2 function on this interval using continuous functions, because we know that we can approximate any L2 function with its Fourier series, at least in the L2 sense. So at least in the mean square sense. So at least in the mean square sense, you can approximate a discontinuous function, even a discontinuous function using continuous functions, any L2 function. You can approximate in the L2 sense, in the mean square sense, using continuous functions. In the examples we looked at, we actually had pointwise convergence. So in fact, even if you have the unit step function, which is not a continuous function, at least it's not continuous everywhere, because it has quite a jump at 0. So we have that Heaviside function, or that unit step function, that's not continuous, but we can approximate it to any degree of accuracy we like with continuous functions, which is quite a remarkable feat. So in our first example, let's let L equals 1, so it looks like the first plot. So in that case, we have f at x equals x from minus 1 to 1. So the Fourier series for f is given by this expression, which we computed, and then here I'm just letting L be equal to 1. So this is the sum, n equals 1 to infinity, of 2 over pi times minus 1 to the n plus 1 over n, sine of n pi x. Now this convergence is in L2, but it is also pointwise. So we know that f at x actually can be achieved in this way. We can actually compute it that way. However, what's important here is we cannot differentiate this term by term. So if you try differentiating f, now remember, what is f? F is just this function. I've circled the domain. F is this function. F at x is equal to x. So if you differentiate it, you're just going to get 1. At least for x inside this interval. Now notice I'm not including either of the endpoints here. We're extending f periodically, so it has a jump discontinuity at every endpoint, which you can see from the graph. If we just go back to the graph for the first example here, so these in the limit, these are all just going to be straight lines like this, and you'll have jump discontinuities in the limit. So in the limit, you're going to have jump discontinuities. So since you have jump discontinuities at the endpoints, the function is not differentiable there. So that's why, if I can go back to this remark, here, we're on remark 3 now. So we start with f at x equals x. We start with f at x equals x on this interval, but when we differentiate it, we stay inside of the interval. So f at x is equal to x on the interval from -1 to 1. So if you differentiate it on the inside of the interval, you're just going to get 1. However, if you try differentiating term by term, so if you start with this Fourier series here, and you attempt to differentiate it term by term, you're going to have a problem. So it's easy enough to differentiate it term by term. So these are all constants here. 2 over pi times -1 to the n plus 1 over n. Those are all constants. So we just differentiate this sine term. Derivative of sine is cosine. Then this n pi comes out. So that n pi comes out. This pi cancels with that pi. This n cancels with that n. And that last cancellation is very significant, because then you have this series, the sum n equals 1 to infinity of -1 to the n plus 1 times 2 times cosine n pi x. This doesn't converge for any x. I say it doesn't converge for any x not equal to 0. It doesn't even converge for x equals 0. Because when x is equal to 0, this just becomes 1, and then this is certainly a non-converging term. So this series does not converge for any x at all. Just period. So it is not possible to obtain the Fourier series for f prime by differentiating f term by term. This is somewhat surprising. We're used to being able to differentiate term by term. And certainly if you have a Taylor series that converges absolutely on its radius of convergence, you're welcome to differentiate term by term as long as you stay inside of that radius of convergence. On the boundary you might not be able to do it, but you can always do it on the inside. But that's not the case with Fourier series. We can't differentiate this Fourier series term by term and get the derivative. So remark number 4, I've also mentioned already. So for 4, an even function has a cosine series. So an even function has a cosine series, and an odd function has a sine series. Furthermore, if f is even, we can compute the Fourier coefficients using these formulas here. So if f is even, then the bn's will all be 0, because with bn you're integrating the even function f against sine. But sine is an odd function, so even function times an odd function is an odd function. If you integrate an odd function over a symmetric interval, you get 0. Furthermore, to get the an's, you're integrating f against cosine. Now f is assumed to be even, and cosine is even, so you have an even function times an even function is an even function. So when you integrate an even function over a symmetric interval, that's the same as just integrating over half of it and multiplying it by 2. So it's the integral from 0 to L times 2. So that just makes your computations a little bit easier if you're dealing with an even function. Similarly, if f is an odd function, then we have these formulas here. So if f is odd, then when you integrate against cosine, you have an odd function times an even function, which is odd. So you integrate an odd function over a symmetric interval, you get 0. Similarly to before, if you integrate an odd function, so now f is odd, sine is also odd. So f is odd, sine is odd, multiply them together, you get an even function. So you have an even function over a symmetric interval, so it just ends up being 2 times the integral from 0 to L. So again, it just makes the computations a little bit easier. Our next remark is remark 5. So again, let's refer to our first example. F at x is equal to x on this interval from -L to L. And we're going to extend it periodically so that f at x is equal to f at x plus 2L for all x in R. Now f can't be an odd function because we have that f at -L is equal to -L, but f at L is equal to f at -L plus L, which is f at L, which is -L again, because again we wanted it to be periodic. So by making it periodic, we've gotten rid of the fact that it's an odd function. Now, it's just at the endpoints, so we can easily deal with that. And the way that we solve this problem is we just redefine it so that it's 0 at the endpoints. So as long as you make your function 0 at the endpoints, then you have something which is periodic and also odd. So, and importantly, it doesn't change f on the inside of the interval, just at the endpoints. And for purposes of integration, which is what you're doing to compute the coefficients, when you compute the coefficients, you integrate. So in terms of integration, it doesn't matter if you're integrating on the open interval or the closed interval. So we just redefine f so that it's equal to 0 at the endpoints. Then we have a periodic function, which is an odd function, and it doesn't affect any of the integrals. So this is a small technicality, but it's just something we do to make sure that the function is periodic and odd. Let's talk a little bit more about odd and even extensions. In particular, let's look at an example, or rather two examples. Let's look at our first two examples. So I'm going to call them examples A and example B, and I'm going to label the functions f sub a and f sub b. I'm using a and b instead of 1 and 2 because if I use f sub 1 and f sub 2, it kind of looks like those orthogonal functions from the last lecture. So we'll call it f at a and f at b. Now, the first one, f at a, that's our first example, which was f at a at x is equal to x on the interval from -1 to 1. So again, I'm picking, this is our first two examples where L is equal to 1 in this case. So L is equal to 1, just to make the computations a little bit easier. So this is the Fourier series that we computed, again with L is equal to 1. Now, f of b is the absolute value of x. Again, I'm letting L be equal to 1. So we have the Fourier series, which we computed, and now we just set L equals 1. Now, what we want to notice here is that these two functions agree for all x from 0 to 1. F at a at x is x, and for all x between -1 and 1, but in particular when x is positive. Now, f of b, when x is positive, the absolute value of x is just x. So we have that f at a at x and f at b at x are the same thing when x is positive. So f at a is what we call an odd extension of f at x equals x. And f at b is an even extension of f at x equals x. The idea here is that you start with a function just defined from 0 to 1, f at x equals x, and then you define a new function, which is an odd function, and we call that an odd extension. So if x is positive, you just define f at a to be f. But if x is negative, so if x is negative, then f, in this case sub a, the odd extension of x will be equal to the opposite of f at the opposite of x, like that. And that ensures that you have an odd function. For f of b, that's an even extension. So in that case, if x is negative, then you define f sub b to be the even extension. You just want that to be equal to f at negative x, like so. Now, if x is negative, we're assuming that x is negative, so when you have a minus sign in front of x, that's actually going to give me a positive number. So that's just a positive number. So x is negative, so the opposite of x is positive. So in this way you can get an odd extension or an even extension. So f sub a is an odd extension of our function. Notice it's just defined, we're just defining f at x equals x for x between 0 and 1. So f at a is defined between -1 and 1. So it's an extension. So if we're defining an extension this way, we don't get the -1, but that's fine. These functions came to us first. We're just talking about how the f at a is an odd extension and f of b is an even extension. But you just want to leave out the endpoints there. Maybe just for clarity, I'll just get rid of the equals. just so we don't have any confusion there. So this means, what does this mean? If we start with this function f at x equals x, defined on the interval x goes from 0 to 1, we can view it as a function that has an odd extension or an even extension. Now the thing about the odd extension f at a, that's a sine series. And f of b is an even function, so it has a cosine series. So what that means is we can take this function f at x equals x, and it's equal to f at a and also f at b between 0 and 1. So that means we can write this function as a sine series or as a cosine series, either one. Now this can be applied to any function f defined on an interval from 0 to L. So you can extend f to an odd function, which I'll call f sub o for odd, on minus L to L, and we can express it as a sine series. Or we can extend f to an even function, which now I'm calling f sub e, on minus L to L, and we can express that as a cosine series, like so. So anytime you have a function which is defined on the interval from 0 to L, you can either extend it to an odd function, which gives you a sine series, or you can extend it to an even function, and that gives you a cosine series. So you have a choice. You can take your function and either write it as a sine series or a cosine series. And then we just restrict the answer to the interval from 0 to L. Because f is just defined from 0 to L, you don't know what's going on with f for x negative. That's not given to you. F is just defined on this interval from 0 to L. We extend it to a new function f sub o or f sub e, and those functions are defined from minus L to L. But in the end, we're only looking at f, which is defined for positive x value. Maybe it represents time, for example. And so then you just restrict your attention back to that interval. So you briefly extend your interest to minus L over L, just so that way you can create the sine series or cosine series. But in the end, you just say, okay, well, the only x's that I'm going to put in there are from my original interval from 0 to L. Let's do an example. So here's an example. Let f at x be this function here. So it's x if x is between 0 and 1, and it's 1 if x is between 1 and 2. So it's, in terms of the graph, it's this object right here. So let me just, so it's just this. Okay, well, I extended that a little too far. It's just that. Because it's only defined on the interval from 0 to 2. So what we want to do is we want to find a sine series and a cosine for series for f that's valid on this interval from 0 to 2. So how are we going to do that? Well, for a, we're going to find a sine series, and for b, we're going to find a cosine series. Okay, so that will come later. Okay, so for the sine series, we're going to extend f to an odd function. So that's what we want to do. So we have our function f here. This is the graph of f. So we want it to be an odd function, so that means it's symmetric about the origin. So you just rotate it until you get something symmetric about the origin. So you just extend it to the left, so it's not the mirror image of what's on the right, but it's the mirror image twice. So first you reflect it through the y-axis, and then you reflect it through the x-axis. Now notice that at the endpoints, which are minus 2 and 2, I'm just defining it to be 0. So now I have an odd function. And then I extend it so it's periodic. So that's what, so it's just repeating. It's just repeating. It's just it doesn't fit on the graph. So we just extend it so it's periodic. Okay, so we have an odd function which is periodic, so that means we can make a sine series for it. So f is going to be equal to this series, this sine series, where the bn's can be determined using this formula. So again, since it's an odd function, we just integrate from 0 to L and multiply it by 2, because f is odd and sine is odd, so you get something which is even. It's even, you're integrating over a symmetric domain, so that makes it just twice the integral from 0 to L. Now in this particular case, L is equal to 2, So notice we're not going to integrate over anything dealing with negative values here. We're just going to integrate from 0 to 2 because L is equal to 2. L is equal to 2. So we're just integrating from 0 to 2. Now that depends, the value depends on whether you're integrating from 0 to 1 or 1 to 2. So that's why we have two separate integrals. We're integrating from 0 to 1, and there f is equal to x. So from 0 to 1, so let me just comment that, so this is f, this is f. Now between 0 and 1, f is equal to x. And between 1 and 2, it's just equal to 1. So you don't see it here, but there's just like a 1 there. So we could actually just write it in. So it's just 1, because it's just 1 on this interval. So it's just 1. Okay, so now we can go ahead and compute these things. And again, it's the usual thing on the left here where we're looking at x times sine of n pi x over 2, so use integration by parts. On the right, you're just integrating sine. So then you simplify that and you get this term here. 4 over n squared times pi times sine of n pi over 2 plus 2 over n pi times minus 1 to the n plus 1. So that tells us that we can write f at x as this sine series. And that's what we wanted to do for A. For B, we want to extend f to an even function and find a cosine series. So once again, here's our function f right here, like so. And now we want it to be an even function, so we just reflect it about the y-axis, so it's over here. And we extend it periodically, so it's just going to continue. So it's just like so. So it goes back up. I could probably actually fit another full period here, so it's going to look something like this, and then just like that, and like that. Oh, well, that's not even. Something like that. Okay. Now, in terms of the integral, we're only going to end up integrating over this interval from 0 to 2. So everything else that we've done to make this an even function, to make it periodic, that's not going to even show up when we integrate, because we write f as a cosine series. And then if you're looking at a cosine series, you can compute the coefficients just by looking at the integral from 0 to L. In this case, again, L is equal to 2, and just multiplying it by 2. So first we have to compute a0, which is just the integral of f. So it's 2 over L times the integral from 0 to L of just f. Now, we don't even have to bother computing that. We can just compute the area underneath the curve from 0 to 2. 1/2 plus 1 is 3/2. So that's just the area under the curve. Now, for n bigger than 0, it's 2 over L times the integral from 0 to L f at x times the cosine term, n pi x over L. L is equal to 2 here. L is equal to 2. So again, we divide it up into two parts. So we have the integral from 0 to 1, where it's x, and then from 1 to 2, it's 1. So I guess once again, I could just put in the 1 here. So f is x from 0 to 1, and it's 1 from 1 to 2. And it's the same sort of computation as before. Here we have an x times a cosine term, so use integration by parts. Here we're just integrating cosine, so some of the things cancel. You just end up with this, 4 over n squared pi squared times cosine of n pi over 2 minus 1. Now this term, cosine of n pi over 2, it's 0 half the time. So it's 0 half the time, and the other half of the time it's either plus 1 or minus 1. But I just decided to leave it like this, so it just looks like that. So the answer here, so this coefficient, so you have the 4 over n squared pi squared. So whenever cosine of n pi over 2 is equal to 1, this is 0. But whenever it's equal to minus 1, you get a minus 2 here. But it's also equal to 0 half the time, and you just have a minus 1. So I just thought it was easier to leave it like this rather than to try to simplify it. So what we've done now is we found a cosine series and a sine series. Notice there's a 3/4 here. That's because remember you have to take a0 and divide it by 2, so that's why there's a 4 there. So we have a sine series here and a cosine series here for the same function. It's for the same function. But you can obtain a sine series by extending as an odd function and a cosine series by extending as an even function, but then you just ignore everything to the left anyway. You just look at what's going on between 0 and 2. So this is valid between 0 and 2, and this is also valid between 0 and 2. So you can either find a sine series or a cosine series. Another thing that you can do is you can expand the Fourier series in terms of exponentials instead of sines and cosines, which sometimes has its advantages. So in order to do this, we have to enter into the realm of complex numbers. So recall that there is a way to write cosine and sine in terms of complex exponentials. So cosine of theta is e to the I theta plus e to the I minus I theta divided by 2. And so in other words, cosine theta is the real part of e to the I theta, whereas sine is the imaginary part. This is really just a result of Euler's formula. So e to the I theta is equal to cosine theta plus I times sine theta. So this formula right here for cosine theta, that's really just saying that cosine of theta is equal to the real part of e to the I theta. And this part, sine of theta, is just the imaginary part of e to the I theta. So you can write it as e to the I theta minus e to the, there's supposed to be a minus sign there, minus I theta over 2i, because the real part is e to the I theta plus its conjugate, its complex conjugate divided by 2. But to get the imaginary part, you start with the number and then you subtract its complex conjugate and divide by 2i, and that gives you the imaginary part. So there's supposed to be a minus there. Let's see if I can just, there we go. I think that's a little bit more visible now. Okay, so the point is that you can write cosine and sine in terms of complex exponentials. So consequently, if you have a function which is an L2 function, you can write its Fourier series, but you can expand all of those cosines and sines into complex exponentials. So you can write f as the sum from n equals minus infinity now to positive infinity. N has to start from minus infinity because you have all of these e to the negative integers that will come out of this. Well, not integers exactly, but e to the in times an integer pi x over L. So you end up with all of these negative numbers here. So for cosine you have negative numbers, for sine you also have negative numbers. So for that reason n has to be negative, or at least you have to allow for negative values for n. So you have this doubly infinite sum now. In this case you can show that the cn's are equal to this expression. So Cn is 1 over 2L times the integral of minus L to L of f at x times e to the minus in pi x over L dx. So there's a negative sign in the exponent. That has to do with the inner product. So we defined the inner product for these L2 functions, but that was for real functions. So if f and g are complex valued functions, the inner product takes on a slightly different form. So the inner product of f with g is the integral from minus L to L of f at x times the complex conjugate of g of dx. We didn't see that before because before we were looking at only real valued functions. So if g is real valued, then the complex conjugate of g is just g, if g is real valued. But now we're looking at complex valued functions. So what that means is that this Cn is equal to f inner product this function, 1 over 2L e to the positive in pi x over L. So we're looking at the inner product of f with this function. Now there's no negative in the exponent, negative sign in the exponent, but when you compute that inner product, you have to integrate f against the complex conjugate of g. So that's why there's a minus sign there. The complex conjugate of e to the I n pi x over L is e to the minus I n pi x over, and that's really a consequence of Euler's formula here. If you compute the complex conjugate of e to the I theta, then that just changes this plus to a minus sign. And then you use the fact that sine is an odd function to put the minus sign inside there. And cosine is an even function. So maybe I'll just write this down. So e to the I theta complex conjugate is going to be cosine theta minus I sine of theta. But then you just write this as cosine of the opposite of theta, because cosine is an even function, you can do that, plus I times sine of minus theta, because sine is an odd function, so it takes that minus sign inside. And now this is e to the minus I theta. So that's why the complex conjugate of e to the I theta is e to the minus I theta. At any rate, when you have complex valued functions, the inner product just requires that you use that complex conjugate. And so that's why there's a minus sign right there. It comes from that complex conjugate. Now notice here that e to the I times a real number has magnitude 1. Once again, that's a result of Euler's formula. Because if you wanted to compute the size of this thing, the size of e to the I theta, that's the size of cosine theta plus I times sine theta. And so what's that going to be? That's going to be the square root of cosine theta squared plus sine theta squared. So it's the square root of that. But of course, that's just by the Pythagorean theorem, that's the square root of 1, which is 1. So in fact, the modulus, or the size, the magnitude, however you want to say it, of e to the I theta, where theta is a real number, is going to give you 1. Now n pi x over L, that's a real number. So this is e to the I theta, where theta is real, so the size of that is equal to 1. So that means that if you compute the L2 norm, you're going to have the integral from minus L to L of something squared, where that something has size 1. So it's just going to be 1. So the integral of 1 over this interval has length 2L, so you're just going to get the length of the interval. So that's why we're dividing by the 2L there. We're dividing by the 2L. So that gives us our coefficients here. What's nice about this is this gives us a very easy way to compute coefficients, because it's very easy to work with exponentials. The downside is that you just end up with complex numbers, which might be difficult when you're trying to solve a problem in terms of real functions. So we just mentioned here that these e to the I thetas, e to the I n pi x over L for n an integer, these give you an orthonormal system, because we saw that the size was 1, because if you divide by the size, so if you look at the L2 norm squared, you get 2L, so that means the L2 norm is the square root of 2L. So you just divide by that. That gives you a normalized function. And you can see that these are all mutually orthogonal. If you just integrate this, that's equal to this product, which you can simplify. This is very easy to integrate, so it ends up being 0 if n is not equal to m, but if n is equal to m, then this is just e to the 0, so that's just 1. So you just end up with 1 over 2L times the integral of 1 over an interval of size 2L, so you just get 1. If n and m are not equal, then this is a periodic function. It's a periodic function with period 2L, so you just end up with canceling terms, so you just end up with 0. Because this is you can write this in terms of sines and cosines, and those have period 2L. So this does as well. That seems like a strange thing to say an exponential has period, but that's because it's a complex exponential. And remember, you can write that in terms of sine and cosine. So let's just make one final comment about the convergence. So we showed that the Fourier series of a square integrable function f converges to f in the L2 norm. Now under certain circumstances, if you add certain smoothness conditions, we can ensure pointwise or even uniform convergence. So here's the theorem. So if f is a piecewise continuous function that has piecewise continuous derivative, then the Fourier series of f converges to f at each point of continuity. So as long as f is continuous, then it does converge, I should say, as long as it's continuous at a point, then the Fourier series does converge pointwise at that point. Now we're making some assumptions here. F is piecewise continuous, but also it has piecewise continuous derivative. So under that additional assumption that it has piecewise continuous derivative, then the Fourier series of f converges to f. And that's certainly true in the examples we looked at. The derivative is piecewise continuous. So that's why in our graphs we were observing pointwise convergence, because the derivatives were piecewise continuous. Now, if in addition f is continuous at all points, so we're still saying that f has piecewise continuous derivative, but if additionally f is continuous at all points and f at L is equal to f at minus L, then the Fourier series converges absolutely and uniformly to f. So it turns out that under these are not trivial conditions, but these are very common conditions for us. We will continually see these kinds of conditions, so we will get at least pointwise convergence, if not uniform convergence. So let's do one more thing just for fun. Summing series using Parseval's identity. So recall that if f has the Fourier series representation that you see here, the usual Fourier series in terms of cosines and sines, what we call the classical Fourier series or the trigonometric series, then Parseval's identity takes on this form. 1 over L times the L2 norm of f squared is equal to a0 squared over 2 plus the sum n equals 1 to infinity of an squared plus bn squared. Now you can use this Parseval's identity to prove some very interesting results about series. So how does that even happen? Well, let's just do an example so we can see it. So let's look once again at our example f at x equals x. Our very simple, straightforward example, f at x equals x. You can get remarkable results from very simple functions. So we actually found a sine series for this function. So we were able to show that f had a sine series, f at x equals 2L over pi times the sum n equals 1 to infinity of minus 1 to the n plus 1 over n times sine of n pi x over L. Okay, so let's let L be equal to pi. So we're looking on an interval of length 2 pi, from minus pi to pi. Now in this case, you get some nice cancellations. So if L is equal to pi, then this L cancels with that pi. So that L cancels with that pi, and this L cancels with that pi. So then the next thing I did is I brought that 2 inside, like that. Now the reason I did that is I wanted to identify the bn's. So the bn's are these terms right here. That's bn. So that's bn. Now the an's are all 0 here because this is a sine series. So an is equal to 0 for all n, including n equals 0. And we have this formula for the bn's. So by Parseval's identity, we can say that 1 over L, but L is equal to pi. So 1 over L is equal to the L2 norm squared of f, or not equal to. 1 over pi times the L2 norm of f squared is equal to a0 squared over 2 plus the sum n equals 1 to infinity of an squared plus bn squared. Now all of the an's are 0, so that term goes away. So that term goes away, and all of those terms go away. So you just end up with the sum n equals 1 to infinity of bn squared. So we can compute all of these things. So the first thing we want to compute is this 1 over pi times the L2 norm of f squared. So that's this. So that's 1 over pi. So that 1 over pi is the same as that 1 over pi. Just for fun, let's highlight all of the pi's. So that 1 over pi is the same as that 1 over pi, is the same as that pi, same as that pi. So, but what is f? F is equal to x. Now we're looking at the L2 norm squared. So that's why we don't have a radical over all of this. So it's the integral from minus L to L, so minus pi to pi, of f at x squared. But f at x is just x. We're just looking at the function. F at x equals x. So we're just looking at f at x equals x. So that's x squared. So you integrate that, that becomes x cubed over 3. So we're integrating from 0 to pi. Now when x is equal to 0, everything goes away. Otherwise you have pi cubed. But there's a pi right here. So pi cubed divided by pi is pi squared. And then we have that 2 there and that 3 there. Okay, so we have 2/3. Fine. 2/3 pi squared. What does that do for us? Well, we also know something about these bn's. We know what the bn's are. So bn is 2 times minus 1 to the n plus 1 over n. But if you square that, the 2 squared becomes a 4. The n squared is n squared. But all of this term, this is either plus 1 or minus 1, but if you square it, it's going to be 1 for sure. So you just end up with 4 over n squared. So you have this 2, well, I guess I've already used orange, so this 2 right there, we square that and it becomes 4. And then in the denominator we have this n, and we square that and it becomes n squared. So what we have is that 1 over pi times the L2 norm of f squared, that's pi squared, 2 pi squared over 3. That's this term right here. So this term right here, that's this term right here, which is 1 over pi times the L2 norm of f squared. Now that is equal, I've already used gray for this, so that's equal to the sum n equals 1 to infinity of bn squared. But we know what bn squared is, right? So that's this term right there. So you're summing it from n equals 1 to infinity. So 2 pi squared over 3 is equal to the sum n equals 1 to infinity of 4 over n squared. So just divide this 4 over here. Now if you divide that 4 over here, you're going to have 2 over 4, which is 1/2. So you'll end up with pi squared over 2 times 3, which is pi squared over 6. But what's on the right? If you get rid of that 4, you have the sum n equals 1 to infinity of 1 over n squared. So the sum of the reciprocals of the square numbers is pi squared over 6, which is a very interesting result that just comes out of nowhere. And we prove that using Parseval's identity and Fourier series representation. So it's a really neat result that perhaps you weren't expecting. So this is something that you can do with Parseval's identity. You can sum very interesting series. You just have to pick them up out of this term right here, out of this term. So if you choose your function appropriately, you can get some very interesting summations. Now you can do this you can find different functions that will give you this kind of result, the sum of n equals 1 to infinity of 1 over n to the p, where p is even. It's not going to work for odd powers, but you can do this sort of thing for even powers. And that's sort of a fun little result that perhaps you don't expect when you're studying Parseval's identity.